Okay, so today we're going to take up the BJT small signal model. Okay, before doing so, I'd like to give you a primer on two-port networks. This is just a short introduction to two-port networks. What is the principle of the two-port networks? Well, this is a network that can be characterized with respect to two sets of terminals or ports, with each port having a voltage and a current variable. So imagine a network N. This can be a very simple network. It can also be a very complicated network, complicated in the sense that there are tens or hundreds of components inside this particular network. Okay, if we want to characterize this network with respect to just two ports, port 1 and port 2, then we can simplify the analysis of the entire system or of the system that employs this particular network. Yun yung principle of two-port networks. So, in other words, if we're just interested in how network N behaves with respect to these two ports, then we can create a simplified representation of this network N, or an equivalent circuit for this network N. Okay, your two ports, typically one port will be the input and one port will be the output. Okay, the principles used in two-port networks can only be applied if this N consists of only linear elements with no independent sources. So hindi pwedeng magkaroon ng non-linear elements dito sa loob ng N. Okay, ano yung mga linear elements na alam ninyo? Can somebody tell me what linear elements he or she is familiar with? What are your linear elements?
Resistor po, sir.
Yes, that's a linear element. Anything else? Resistor lang ba? Okay, your capacitor and your inductor are also linear elements. They're linear elements because the response of a capacitor or an inductor can be described by a linear differential equation. So those are also linear elements. The other linear elements are your linear sources. Your linear sources can be a linear dependent source or a linear independent source. But in the case of two-port networks, you are not allowed to have independent sources inside N. In other words, hindi pwedeng magkaroon ng voltage source dito or current source. Pwede magkaroon ng dependent sources, voltage-controlled voltage source, voltage-controlled current source, current-controlled voltage source, current-controlled current source. Pwede yan, ano? Pero hindi pwedeng independent. Okay. So the parameters of a two-port network completely describes its behavior with respect to the input and output variables. And I mentioned this already. This allows large systems to be broken down into building blocks, where each block only needs to be represented by its two-port parameters. So when you have a complex system, you don't want to analyze the system as a whole. It might be too complicated. So you try to break this up into building blocks. You partition this into building blocks, and then you characterize each building block with its two-port network, and then the overall system will now be easier to analyze. Now, the parameters of a two-port network depend on what are considered to be the independent and dependent variables. And I'm going to give you one example. If the independent variables are I1 and I2, and the dependent variables are V1 and V2, the network can be characterized by what are called its open circuit Z parameters. Okay? So again, we have four variables, V1, I1, V2, I2. Two of these will be independent and two of these will be dependent. Okay? Kung yung independent natin are I1, I2, and the dependent are V1 and V2, that means that we can express our dependent as a function of our independent. So kung ginawa ko yan, V1 will be a function, let's say F1 of I1 and I2. And V2 will also be a function, let's call that F2 of I1 and I2. Okay, so these are my dependent. Dependent kasi nagde-depende siya dito sa I1 at I2, no? Itong dalawang to magde-depende sa I1 and I2. And then these are my independent. Okay, and if the independents are your currents and your dependents are your voltages, you can characterize the entire system in terms of just 4 parameters, and these are called your Z parameters. Okay, let me write out the equations that will govern this particular network. Okay, your V1 is going to be equal to Z11 I1 plus Z12 I2. Okay, and your V2 is going to be Z21 I1 plus Z22 I2. Okay, where your Z of, let's say, XY, ZXY, no, X being 1 or 2, Y being 1 or 2, these are your, we call this your open circuit Z parameters. Those are called your open circuit Z parameters. Now, why are they called your open circuit Z parameters? Okay, let's say we want to evaluate Z11. I want to evaluate Z11. The way I do it is this. So let's say this is my network. Okay, just to show that they're characterized by the Z parameters, I just put a Z here. Okay. So this is I1 and this is I2. Okay. What I'm going to do is I'm going to place a test voltage here, which I will call D1. So this is a test voltage. Now this should not be new to you. In EEE 123, remember, sometimes to determine the input resistance of a circuit or the Thevenin resistance of a circuit, sometimes it is necessary to apply a test voltage. Not all the time can you get the input resistance by just getting the equivalent resistance with respect to a set of terminals. Sometimes it's necessary to apply a test voltage. So we're going to put a test voltage here. And here, no, this is V12, this is V2. I'm going to leave open circuit. If I leave that open circuited, then I2 will be equal to 0. Kasi bukas to. Bukas yan, ano? May value ng V2 dyan, pero bukas siya. So I2 is going to be equal to 0. Okay? If I2 is equal to 0, if you take a look at this equation, no? V1 is Z11 I1 plus Z12 I2. This is now going to be equal to 0. So we now say that Z11 is just V1. Kung ano man yung value dito na kinabit natin, itong test voltage, divided by I1, which we have to determine. You have to determine I1, okay? This might be there's a circuit inside here. After applying this test voltage, you have to determine ano yung value ng I1, and that is how you will get Z11. So this is V1 over I1, and just to qualify that this is open circuited, we say this is evaluated at I2 equal to 0. No? So that is to signify that we left this open circuited. Okay, notice that V1 over I1, this is volts over amperes. The units is ohms. No? This is the units is ohms. And that's why we call it an impedance. It is called an impedance. And we call it open circuit impedance because to determine any particular quantity of Z, then you have to have one side or the other side left open circuited. So depending on what you want to evaluate, for example, if I wanted to evaluate Z12, then I would have to open circuit my port 1 and apply a test voltage at port 2. So that's how I will implement Z12. If I apply a test voltage at port 2, I will be able to determine I2. No, applying a test voltage at port 2, I will be able to determine I2, and Z12 is just V1 over I2. Just because port 1 is open circuited does not mean there's not going to be any voltage. You know? Remember, there's such a thing as an open circuit voltage. So that's how you determine your Z parameters. Okay, and what will your model now look like? Okay, note that this actually look like KVL equations. Pag tinignan nyo to, this is a voltage. Impedance times current is voltage. Impedance times current is voltage. No? So that's true for both V1 and V2. Okay, so let's take a look at port 1. Port 1, I have V1. I have a current flowing I1. What will represent this voltage drop? That will be represented by I1 flowing through Z11. No? So I have here an impedance equal to Z11. So I1 flowing through Z11 will represent a voltage drop across Z11, which is Z11 I1. And then I have to add another term. No? I have to add this term. Okay. Note that the voltage generated by this term is controlled by a current that is outside of the circuit, no? Outside of the port 1 circuit. Meaning to say, this term must be from a controlled source. Right? So this is going to be a controlled source. Okay, this is going to be Z12 multiplied by I2. And you have something similar on the other side. Okay, this is going to be Z21 multiplied by I1. This is going to be Z22. This is V2. And this is I2. So if I get KVL in this loop, I'm going to get the second equation. If I get KVL on this loop, I'm going to get the first equation. Now, I normally have a common reference for V1 and V2. Thus, this would have to be shorted to that, so that my reference for V1 and V2 will be common. That is not an absolute condition, but that is the usual case, that your reference is the same. So note that, again, this can be a very complicated circuit. Pwedeng komplikado to. But we can now represent it by this much simpler model. And we can now plug this model wherever we use the original circuit and use this model to characterize now the behavior of the bigger circuit where this belongs to. Okay. So this is an example. Any questions? Any questions? Okay, so depending on what are considered the independent and dependent variables, there are many other common two-port network parameters. So I'm just going to name this. Earlier, I introduced to you the Z parameters. So your independent variables are your currents and your dependent variables are your voltages. The Y parameters is the converse, no? Your independent variables are your voltages and your dependent variables are your currents. And if you work out the equations for the Y parameters, you're going to find that the parameters are always a ratio of current to voltage or Siemens. That's why tinatawag siyang Y parameters. Yung H parameters, hybrid yun. Some of your parameters are current, some of your parameters are ohms, some of your parameters are Siemens, and some of them are dimensionless. So yun yung H parameters. And then you also have ABCD parameters. Anyway, I'm not going to go through all of this. You're going to learn more about two-port networks I assume in future courses. I just wanted to introduce you to two-port networks because when you take up amplifier circuit analysis in module 5 and also frequency analysis in module 6, everything will be done using two-port networks. So you have to have some familiarity with two-port networks. Any questions? Any questions so far? Okay. If I'm going a little bit too fast, just signal me, to slow down, or you can stop me anytime if you want me to expound further on anything that I just said. Okay, what do I want to do at this point? What I want to do is I want to model the transistor as a two-port network. Just the transistor. So ang objective ko ngayon, I'll give you an example. Let's say the common emitter transistor. So what does a common emitter transistor look like? I showed that earlier, or we analyzed this earlier. Okay, that looks something like this. Okay. So I have an input. My input is I sub B. Okay. My input current is I sub B. My input voltage is VBE. Okay. My output current is I sub C. And my output voltage is VCE. So this is just the transistor, nothing else. Transistor lang yan. Walang resistor, walang kahit ano na kabit. What I want to do is I want to model it as a two-port network, where I have an input side, VI I sub I, and I have an output side, V sub O, I sub O. Okay, can we do this? Yes, we can. But there are certain constraints. First of all, I mentioned earlier that for a two-port network, you can only have linear components inside. And we know that a transistor is not exactly linear. The principal behavior of a transistor is exponential. You know that from its large signal model. It's exponential. Okay? An exponential function is not a linear function. It is not a linear function. So for me to be able to represent my transistor as a two-port network, I have to linearize my transistor. And that is possible if I make my input variation very small. If I make the changes in my input, in this particular case, if I make VBE very small, then I can linearize this particular transistor and represent it using a two-port network. Now, if the changes in VBE are small, then we are now dealing with a small signal model. Okay, is that valid for a transistor? Can we say that we are dealing with a small signal model? Fortunately, yes, because particularly for a BJT transistor, your gains are very high, and therefore the input signal is usually quite small. If you recall, for example, the homework that I gave, you're dealing with input changes in the millivolts, and you get large changes in your output, but your input changes are only in the millivolt. So yes, it is valid. That is a valid condition for your BJT. Now, because this is now linear, okay, you can use all of the techniques that you learned in EEE 123 for linear circuit analysis. Lahat ng pinag-aralan nyo sa 123, pwede nyo gamitin. If you insisted on using the nonlinear model of the transistor, which is the exponential model, okay, imagine a circuit with many, many transistors, and then each transistor you use the exponential model. The only way you would be able to solve the problem is using iteration, because there's no way you can come up with a closed form for the solution of the voltages and currents in that particular circuit. That is, if you're using the exponential model. Hindi nyo magagawa. No? The only way you can do that is through iteration. Imagine a system of equations na puro exponential, and then you're supposed to find the unknowns. No? That can only be done by a computer. In fact, that's how simulators often work. But if you were to do pencil and paper calculations, you would not be able to do it. But because we now make this a linear model, pwede na kayong gumamit ng nodal analysis, ng network simplification, ng superposition, Thevenin's theorem. You can now use all of that, no, to analyze your circuit. Okay, what other constraints are we going to apply? We will assume what we call a unilateral model. In a unilateral model, the input affects the output, but the output does not affect the input. Now, this is not always true. There are a lot of instances where the output will affect the input. Itong example na binigay ko earlier, this is not unilateral. This is not unilateral because what is happening here will affect my input. Kasi kung may I2 ako rito, kung magbago yung I2, which is part of my output, magbabago ito, no? This is J1 to I2, and therefore my input will be affected. So this is not unilateral. But for a transistor, we will assume a unilateral model. Okay, now my independent variables are my input and output voltage, and my dependent variables are going to be my input and my output currents. So you can think of it this way. So these are my equation, these are my functions. No, let's call this F1. This is F2. So these are my dependent variables. Okay. These are my dependent variables. And then these are my independent variables. Okay, so I will be able to describe this network using these two equations. One, describing the input, I1, I's of I, and one describing the output, I's of O. Okay, however, because we are assuming a unilateral model, okay, this V's of O is not going to affect I's of I. Okay, so ito mawawala. And then I'm just going to end up now with I's of I, which is a function of V's of I, and I's of O, which is a function of both V's of I and V's of O. So magiging bahagyang mas simple yung model natin. It's going to be a little bit simpler. Now, as I mentioned, There are some limitations to the unilateral model, but for the moment, it will suffice for what we are going to use it for, this unilateral model. Any questions with regard to this assumption of unilateral behavior? Any questions? Again, unilateral means the output should not affect the input. Okay, so let's try to determine the small signal model of the NPN common emitter BJT. Okay, and our starting point is going to be the large signal model. I just want to ask, have any of you already viewed the recorded lecture of Professor De Leon, of Dr. De Leon, on this topic? Meron na ba? Can I can I have a show of hands? Don't be shy if you to admit that you haven't. No, I know that we're all very busy, so di pa masyado. Wala pa? Most of you haven't, ano? Yung iba ayaw yata sumagot, nahihiya, no? Okay. Please view that recorded lecture, no? Because the way Dr. De Leon derived or linearized the transistor is a more how do you say it? A more thorough discussion of the subject matter, no? What she did was she developed the linearized model using Taylor series expansion, which is a more rigorous method for doing it. It's a more mathematically viable or more mathematically sound method for doing it. Gumamit siya ng Taylor series expansion. What I'm going to do in deriving the small signal model is going to be a little bit more intuitive. It's not going to be as mathematically rigorous. No, my objective is just to give you more of a feel for why the small signal parameters that we're going to derive are valid. Okay, but again, if you want a more rigorous explanation, please listen to the lecture of Professor De Leon, the recorded lecture. No, I think it's a very good lecture. Okay, so again, no, I'm going to try to model this as a two-port network. Ang mga linagay kong variables dito are still capital subscripts. Ano? Notice that the subscripts are capital. V capital C capital E, I capital C, I capital B, V capital B capital E. Meaning to say these are still total signals. And I have this relationship. So this is the refined large signal model of my NPN transistor. It describes the output as a function of two inputs, my base to emitter voltage and my collector to emitter current. So medyo consistent yan with this. Okay? So this is, lumalabas, this is I sub C, and then this is VBE, and then this is VCE. Okay. I sub C, my output being a function of my base to emitter voltage and my collector to emitter voltage. Okay. Collector to emitter voltage, I think might have said current earlier. Okay, I can plot this. Let me disregard first this term. In other words, let's assume that VCE is constant and will not affect the shape of the plot. So we plot this for a constant value of VCE. Okay, my plot will look like the diode curve because this is just Shockley's equation. So this is how my plot is going to look like. And my transistor is going to operate at a certain operating point. So this is the operating point or the Q point, where my base to emitter voltage is VBEQ, and my collector current is going to be ICQ. VBEQ versus ICQ. By the way, this is also called the transfer characteristics of your circuit. Earlier transfer characteristics. Ang ibig sabihin ng transfer characteristics is a plot of your output versus your input. Earlier we did transfer characteristics where both output and input were voltages. But in this particular case, our output, which is the independent variable, which is the dependent variable, is a current, and the input is a voltage. So these are also transfer characteristics. Iba lang yung quantity ng output at saka ng input. So the plot will look like your diode plot. And this Q point has to be established by your biasing circuit. So yung biasing circuit, we treat that separately. Remember, we are now splitting the analysis into two parts. One is the bias and the other is the small signal. So we would have computed for ICQ separately through the biasing circuit. Now, for small input changes, the slope of the transfer characteristic curve in the vicinity of the Q point can be considered constant. So this is how I show that. Let me just blow this up a bit. Let us say that this is my input change. This is my small change in VBE. Okay, this is my Q point. So this is my small change in VBE. What I am saying is the black curve, which is the actual characteristic, can be approximated by the blue curve, which is a straight line. Or the black curve can be considered to have a constant slope. Yun yung sinasabi ko rito. The black curve can be considered to have a constant slope in the vicinity of the Q point. In other words, habang gumagalaw yung operating point ko rito, because of my input change, okay, the response will be practically linear. So how will my output change? Okay, this is how my output will change. So this is going to be my I small c. The change in output with respect to my change in VBE. Okay, and I am saying that we can use, okay, this blue curve to approximate that change. That is what I am saying. Okay, I show it again here. So notice that I now apply a time varying component to my or I superimpose a time varying component on my Q point. So that time varying component is now V small be. Again, take note of the subscripts. At this point of the course, the subscripts are very important. It will tell you whether you're dealing with the total signal or you're dealing with the time varying component of the signal. So let's say I have VBE, which is a positive increase in the value of V capital E, just a positive increase. Okay, that will result in this particular change in I sub C. It is also a positive increase in I sub C, and that change will follow this curve, the blue curve. Right? Let's assume that the slope of that curve is equal to M. So it's really just interpolation, di ba? Kung meron kang initial point, alam mo yung slope, you know the change in the input, you can determine the output. Simple interpolation. Okay, now what will happen if I make this VBE approach 0? Okay. In other words, gawin kong maliit na maliit itong VBE so that halos 0 na siya. What is my expression for slope going to be? I'm trying to compute for the slope. This is going to be the expression for my slope. my slope M is the limit as VBE approaches 0 of the change in I sub C. So ito yung change in I sub C. So from this point, it will jump to this point, no? From this point to this point. With respect to the change in VBE, the change in VBE is the jump from this point to this point, this small change in VBE. Okay, so itong I sub C na to, that is the I sub C at this value. Samantalang itong ICQ, that is the I sub C at VBEQ. So we get the difference. And then ito naman sa baba, this is the change in input. So this is VBEQ plus V small e minus VBEQ. Actually, magka-cancel out to. This and this will cancel out. And ang matitira is just VBE sa denominator. Okay, who can recognize what this looks like? Anyone? What does that look like?
Derivative po, sir.
That's right, no? That looks like the formula for the derivative of this curve at this point. At this point. Now, since I sub C is a function of two variables, it's a function of VBE and VCE, then we don't use derivative, but we use partial derivative. Because yun nga, no, I sub C is a function of two variables. So the slope is actually the partial of your collector current. Again, no, we're talking about large signal here. No, we're talking about this curve, which is large signal. So your subscript is capital with respect to VBE, evaluated at the Q point. This is evaluated at the Q point. That is the slope of this line. So now, knowing the slope of that line, if I wanted to interpolate the change in I sub C with respect to VBE, then I just use this formula. The change in I sub C, again, note now this is a small letter because it is only the change. The change in I sub C will be equal to the slope multiplied by the change in VBE. Again, note that this is small letter, where I small c is the change in I capital C as a result of a change in V capital E. Any questions? Any questions? So do you understand this idea of interpolation? I hope, no? Walang reaction. I hope you understand this idea of interpolation. Okay, what we're going to do is this, no? We're going to define the term transconductance. Itong slope na to, we will call that the transconductance of the transistor. So that is the partial of IC with respect to VBE evaluated at the Q point. And for small changes in VBE, the change in I sub C will just be your transconductance multiplied by VBE. Now, why do you call it a transconductance? First of all, the units. What is the unit? Current over voltage. What is the unit? Ano magiging unit niya? Come on, guys.
Siemens po, sir.
Okay, Siemens, no? Unit is Siemens. So it is a conductance. Okay. Now, why do you call it a transconductance? It is called a transconductance because the voltage is not in the same circuit as the current. The voltage is not across the same element as where the voltage is in another part of the circuit, basically. No? The voltage and the current are not within the same circuit. The voltage is in another part of the circuit. That's why it's called a transconductance. If the voltage and the current were across this were associated with the same element, it's just called a conductance. Okay, but the voltage is not associated with the same element, no? So it's a transconductance. Okay, now we can determine G's of M. No, we can determine G's of M by just getting this partial derivative. Okay, and what we're going to use is the large signal BJT model. No? Now, in determining GBM, to make it a little bit easier for us, we're going to neglect the early effect, and we're going to assume that VBE has a normal value. So you recall our equation is I sub C is equal to I sub S e to the VBE over V sub T minus 1. Then you have 1 plus VCE over V sub A. So we neglect early effect. So wala na to. Okay. And then if we assume that VBE has a normal value, then this is also going to be negligible. E to the VBE over VT is going to be much greater than 1. So ang matitira na lang ito. I should use a small I, sorry. No? Ang matitira na lang is this. Okay, so I need to get the partial of this, no, with respect to VBE. That's what I want to do. Okay. The partial of IS e to the VBE over VT with respect to VBE. What is this? No? This is I sub S, the partial of e to the VBE over VT, okay, with respect to VBE, because I sub S is a constant. What is the derivative of an exponential? It is also an exponential, but we have to get the derivative of the argument of the exponential. No? So this is going to be I sub S, okay, 1 over V sub T e to the VBE over V sub T. So that's exactly what I got here. That's what you get here. But you have to evaluate that at VBE equal to your quiescent point. Okay. At VBE equal to your quiescent point, your numerator ends up just being ICQ. No? Because I sub S e to the VBEQ over V sub T is just ICQ. And so I am now left with this. My transconductance is just ICQ over my thermal voltage, V sub T. So G sub M is ICQ over V sub T. IC is G sub M multiplied by VBE, or ICQ over V sub T multiplied by VBE. Okay. That is how your collector current will change with respect to a small change in VBE. With respect to a small change in VBE. Now, how do we take changes in VCE into consideration? Because we said our collector current changes with both VBE and also with VCE. No? So we can follow exactly the same procedure yung ginawa natin just now for changes in VBE. Gawin din natin for changes in VCE. So our starting point is going to be this equation. Following the same principle, okay, for small changes in VCE, the change in IC will be the slope. So this is the slope, which we consider constant at VCE equal to VCEQ multiplied by my change in VCE. Now, what function, what characteristic curve are we using here? No? This is now your output characteristic curve. What we're using now is your output characteristic curve. This is your I sub C versus your VCE. Right? And you know how this looks like, no? These are your collector curves that look something like this. Okay, where this might be your VBEQ. This might be the base emitter voltage at quiescent, no? And this might be your operating point. No? So this is going to be VCEQ, and you're going to have an ICQ here. So that is your quiescent output voltage and your quiescent collector current. So we're saying that for small changes in VCE, ito yung maliit na change in VCE. Okay. This can be considered a straight line. Well, I just messed up, no? But that can be considered a straight line. And in fact, it really does look like a straight line. No? Mukhang straight line din talaga siya. And we can use the slope. We can use the slope of this line at this point at VCEQ to now determine how much your IC will change when VCE changes. So we're doing exactly the same thing. That's exactly what we're doing here. Okay, itong term na to, this term, we're going to define that as our output conductance. Again, it's a conductance because it is the ratio of a current to a voltage. Okay, this time the current and the voltage are in the same circuit. Okay. So it's not a transconductance, it's a conductance because the current and the voltage are in the same circuit. And if I compute for G sub O, so I just get the partial of I sub C with respect to VCE. So if I'm differentiating I sub C with respect to VCE, this term is going to be a constant. So pwede nating ilalabas natin to, no? And then you now have to get the derivative of this with respect to VCE. The derivative of 1 is equal to 0. The derivative of VCE over V sub A is just 1 over V sub A. Right? So lalabas, the only thing that will be left will be this divided by V sub A, which is this. That is the value of G sub O, your output conductance at your operating point. And then if you take a look at your numerator, this is nothing more than your quiescent current, ICQ. So finally, ito lang yung magiging formula natin for your output conductance, G sub O. So output conductance is ICQ over V sub A, ICQ over V sub A, and your change in collector current due to a small change in collector to emitter voltage will be G sub O multiplied by VCE. Okay, more often, instead of output conductance, we use output resistance, R sub O, and output resistance is just 1 over output conductance. So I can express this change in terms of G sub O, so that's G sub O times V sub E, VCE, or in terms of R sub O. It's VCE over R sub O. Either way, I'm going to get this formula, VCE multiplied by ICQ all over V sub A. So again, this is the change in collector current due to a change in VCE, okay, using the slope of the output characteristic curve at the operating point to approximate the change. actually it ends up, it's not really an approximation anymore, because remember we made our limit approach zero. No? When we make our limit approach zero, then it's already exact, hindi na approximation. Okay, now may model na tayo for the output. No? We already have a model for the output. Remember, yung isang gusto nating makuha is yung output characteristics. So this is I of C, that is a function of VBE and VCE. No? So ngayon, ang kailangan natin is a model for the input. So this is I of B as a function of VBE. No? Bakit nawala uli yung VCE dito? Can somebody tell me? I just want to check whether you've been listening.
Sir, unilateral po.
Exactly, no? Because unilateral. We don't expect the output to affect the input. So ito na lang yung kailangan natin to complete our model. So this is modeling the C amplifier input. No? So the small signal source has to supply a current when it is connected to the amplifier input. And the amplifier input can be modeled by an input resistance, which we call R of pi. In other words, if this is our transistor model, okay, so this is our transistor model, okay, so ganyan yan. Let's say magkabit ako ng signal source dito. Okay. Of course, a current is going to flow. What is this signal source going to see? So this is my V of S, no? This is my signal source. What is that going to see inside here? What is going to see inside there is, in effect, a resistor. And that resistor is going to be what we call R pi. Now, why pi? Later on, you're going to find that the model, we call it the hybrid pi model. And therefore, the input resistance, we call it R of pi. So ang makikita nitong signal source na to, if this is the transistor model, it's going to see a resistor, and that resistance is going to be R pi. Remember that this does not have any independent sources inside. This does not have any independent sources inside. No? When you have a circuit with no independent sources, then if you get the input resistance at any port, it will always be just purely resistive. Or rather, if you get the Thevenin equivalent at any port, it will be purely resistive. Dapat natutunan nyo yan sa 1, 2, 3. Magkakaroon ka lang ng Thevenin voltage kung meron kang independent source inside your circuit. But if you have no independent source inside your circuit and you try to get the Thevenin equivalent with respect to any port, what you will see is a resistance. And so that's what this will see. Okay, so how do we compute for R of pi? R of pi is just the rate of change of I of B with respect to VBE. The rate of change of I of B with respect to VBE. Now, ang unang inclination natin would be to take a look at the input curve. No? The input curve is your I of B versus VBE. But it turns out we don't really have to do that. Why? No? Because I of B is I of C over beta. So itong I of B na to, we replace with I of C over beta. So I'm going to come up with this, no? This expression for 1 over R of pi. 1 over beta, the partial of I of C with respect to VBE. But if you take a look at this, we already have a term for this. We call this our transconductance. So you remember that G of M is equal to the partial of I of C with respect to VBE. This is at the Q point, evaluated at the Q point. So this is our transconductance. So 1 over R of pi is simply G sub m over beta. Or R sub pi is just beta over G sub m. That is the resistance that will be seen by a signal source when I connect the transistor input to it. It will see a resistance equal to beta over Gm. So now I have a complete picture. Right? Ito na yung first equation ko. You remember yung first equation ko? Ito, no? This first equation. And then I now have this second equation. Where G sub m is this, ICQ over V sub t. And this you'll have to remember, no? For example, this is something that usually dapat alam nyo by heart when you're analyzing the circuits, this formulas, ano? G sub m is ICQ over V sub t, G sub o is ICQ over V sub a, then R pi is beta over G sub m. Hindi naman mahirap maalala. Okay? G sub m ICQ over V sub t, G sub o ICQ over V sub a, and then R pi is beta over G sub m. Now, what does our model look like? What will our model look like? Okay, if you take a look at this looks like a nodal equation. You have current I sub c, which is my output current, consisting of two components. So presumably, this is the current flowing in one branch, and this is the current flowing in another branch, and the total current from those two branches will comprise your I sub c. So if I try to model that, I have, okay, let's say this is C. Okay, so this is now my VCE. Again, small signal model to, kaya VCE has to be small c, small e. This is now wrong direction. This is now I sub c. So I sub c will flow into two branches. Okay, it will flow into two branches. Ganyan. Okay, one is flowing through a resistance 1 over G sub O, or R sub O, no? 1 over G sub O, where the current flowing through this conductance, or through 1 over G sub O, or the voltage rather flowing, the voltage across this conductance is VCE. Okay, so I can model this as a resistance. Let me just call this R sub O, where R sub O is 1 over G sub O. No? The voltage across R sub O is VCE. So that takes care of this term. No? And then I have another current, G sub M VBE. But VBE is in another part of the circuit. And therefore, that must be a controlled source. That must be a controlled source. Okay? So the current is downward, and this is now G sub M VBE. So that takes care of my output. Now, what about my input? My input is, ang nakikita lang ng input ko is a resistance, no? Equal to R pi. So my input is at my base. So this is my base. That's my input. What it will see is a resistance equal to R pi. Okay. This is my emitter. This is also my emitter, and therefore these two must be connected this way, which makes sense. That's why you call it a common emitter, because the emitter is common to both the input and the output. Right? And this is now going to be VCE. BE. And so I sub B is just simply VBE divided by R pi. Okay. So this is now my model. Okay. This is what my transistor is equivalent to. This is just the transistor. Walang nakakabit na resistance, walang kahit na ano. Just the transistor by itself. If we're doing small signal analysis, that is, if we're only considering small variations in the input signal, and if it is properly biased, that is, it is biased in the forward active region at an appropriate bias point, then we can use this model to compute for voltages and currents, as long as the variations in the voltage, the inputs are very small. We can use this to compute for voltages and currents. And you can use all of the techniques that you learned in EEE 1, 2, 3. You don't have to solve any equation iteratively, walang exponential equation, okay, walang ganon. So it's just going to be all nodal analysis, for example, or network simplification, or Thevenin's theorem, or whatever. Are there any questions? Any questions? Okay, so just to summarize, this is the NP and BJT common emitter small signal model. Now, may qualifier dito, no? At low frequencies. Bakit at low frequencies? Because we are not taking into consideration capacitances that exist in the transistor. The transistor has internal capacitances. Every time you have a junction, you have a capacitance because you have charge displacement. No? Pag may PN junction ka, there are charges that are displaced, and therefore you have a capacitance. Now, a capacitance at low frequency is like an open circuit, so you don't have to take it into consideration. But as your frequencies get higher, okay, the impedance of your capacitance becomes smaller. Okay. Habang tumataas yung frequency, lumiliit yung impedance ng capacitor. At zero frequency, which is DC, the impedance of your capacitor is infinite, no? Because it's 1 over omega C. If omega is equal to 0, you have infinity. Habang tumataas yung frequency mo, lumiliit yung impedance ng capacitor. And it's now going to affect the voltages and currents here. So we only use this model at low frequencies. When we go to Module 6, frequency analysis, doon papasok na yung mga internal capacitances. And when we include the internal capacitances, you're going to see that the model looks like a pi. No? Pi. That's why this is called your hybrid pi model. So the model is linear. It's much easier to use than the large signal model. It fully describes the response of the BJT to small signal variations around the quiescent point. It can only be used for the time varying or AC component of the input. Remember that your parameters, GM, R pi, RO, are dependent on the Q point. And remember that this is unilateral. It's obviously unilateral kasi kahit na ano mangyari rito, whatever is happening here, walang effect dito sa kaliwa. Dito sa kaliwa, what will affect I sub B is just R pi. Okay? Unlike here at the output, your output is affected by your input because of this, because of your GM VBE. So that is your transistor model. Okay, we developed this model for the common emitter, configuration. Fortunately, you can plug in this model for the transistor, even for the other configurations. In other words, itong model na to, okay, this is your base, this is your base, this is your collector, this is your emitter. As long as I make the correct connection to your collector, to your base, to your emitter, then I can use this model even for your other configurations. So this is the only model that we're going to be using. No, we're not going to derive a similar model for your common base or your common collector. Ito na lang ang gagamitin natin. No? The common emitter was chosen as the base model because it is a high gain model. It is the highest gain model. No, although the common base has a similar gain actually. No? But anyway, that might have been an arbitrary choice. So ito lang yung kailangan nating tandaan. No? When we will analyze now even the other transistor configurations. Now, later on, you're going to be adding resistors to your transistor network. In fact, later on, even capacitors. Then magkakaroon na ng mga elements outside of this. No? So kung magkapit ka ng collector resistor, you're going to have a collector resistor connected to ground, for example, or what have you, a base resistor. Magkakaroon ka ng elements outside of this that you're going to have to connect to this model. And then you're going to have to derive what will be the new parameters of your two-port network. So that's what's going to happen starting module 5. Using this as your base, kapag nadagdagan ka na ng mga elements, then you're going to have to derive what will be the new parameters of your two-port network. Any questions? Questions? Okay, one last thing I wanted to discuss, no? Because what about the Pnp transistor? And this is quite important. What is the model, two-port model of your Pnp common emitter transistor? Okay. So you recall yung common emitter Pnp transistor natin looks something like this, no? So our emitter is the common terminal. Okay. The way we draw it, we draw the emitter on top. Okay. So this is our base, this is our emitter, and then this is our collector. Okay. So what you have here is instead of VBE, you have VEB. Okay. This is now small e, small b, no? This is a small signal. Here you have VEC. Okay. And then your current is this direction. No? This is I's of B. And then your current here is this direction. This is I's of C. Okay. So nagbaliktad yung direction of current, and then yung subscripts natin for voltages natin nagbaliktad din, no? Which sanay na naman tayo sa BJT, no? When you have a PNP, nagbabaliktad, no? The same way pag MOS, pag P-channel MOS, nagbabaliktad din yung subscripts natin. Otherwise, our formulas are the same, no? For example, G's of M, this is equal to the partial of IC with respect to VEB. So imbes na with respect to VBE, this is with respect to VEB. Okay, where the formula now for IC is equal to, okay, this is neglecting early effect, and then assuming nominal values of VEB. This is IS e to the VEB over V of t. And if I compute for this at the quiescent point, no, this is at VEBQ, and you can try this at home, but you don't have to because it's quite obvious. you're going to get exactly the same formula. You're going to get ICQ all over V sub t. So it's the same formula for your NPN and your PNP transistor, the formula for G sub M. Same thing with G sub O. If I compute for G sub O, this is my output conductance, I'm going to get the same thing. I'm going to get ICQ over G sub A. So G sub O is the partial of IC with respect to VCE. So pag kinuha mo yung G sub O, now you have to consider early effect, no? Kasi nandun na yung VCE. And I'm going to get the same formula as my NPN. And even R pi, I'm going to get the same formula. This is beta over G sub M. Okay. And so what are my equations going to look like? No, my equations are my model equations, I sub C. The change in collector current is going to be G sub M multiplied by VEB plus G sub O multiplied by VEC. And I sub B is just VEB all over R pi. So again, nagbaliktad lang din yung subscripts ko. So let me draw the model. Let me draw the model. Okay, so I'm going to draw my E up here. So this is going to be my E, my emitter. Okay, my current is going to be flowing this way. No, that is IE. There are going to be two components. One is going to go through G sub O. Okay, and then the other is going to go through a controlled current source whose value is G sub M VEB. And then it's going to flow out this way. So this is my collector. So here, no, I sub C will be composed of the current flowing down here plus the current flowing down here. And then this is now going to be VEC. And then between E and B is just R pi. And this is going to be, this is my base, this is VEB. Okay, what I'm going to do is, let me flip this. No? If i-flip ko lang, para yung emitter ko nasa baba, yung collector at base ko nasa taas. Okay, so flip natin siya. Okay. So drawing ko muna yung base. Okay. So this is my emitter. This is R pi. Okay, this is going to be, okay, yung emitter ko is plus, right? Minus, this is VEB. VEB. Okay, what if I wanted my base to be positive with respect to my emitter? Then all I have to do is reverse my subscripts here. So instead of writing this as minus plus VEB, I can write this as plus minus VBE. So let me do that. I could have written this as plus minus VBE. The two are the same. Okay, dito ngayon tayo sa output side. So this is my emitter, this is my collector. Okay, this is plus minus VEC. Again, I could make this plus minus VCE. Okay. By the way, this is 1 over G sub O or R sub O, no? 1 over G sub O. Okay. And so this is, let me just say R sub O, no? Understood na R sub O is 1 over G sub O. So that takes into account now the current here. Okay. Now let's take a look at this, no? Ito magiging paganyan. Okay? Where this is GM VEB. What if I make this VBE? If I make this VBE, then itong direction ng current magiging pababa. Magiging pababa. So let me do that. No? So ito, oh, sorry. This one, I make this VBE, and now I can change the direction of current so that this is going down. What do you notice about this? What do you notice about it? Anyone?
Same lang po sa NPN.
It's exactly the same as the NBN. If you take a look at this and this, it's exactly the same. In other words, there is no need for a different small signal model for your PNP transistor. Whatever the small signal model for your NPN transistor, that is also the small signal model for your PNP transistor. Okay. Ang nagbabago lang sa PNP transistor is when you do bias computation, when you're computing for the bias point. But when you're doing small signal analysis, the circuit that you use for your PNP and your NPN are exactly the same. So that's it. That's my presentation to you of small signal, the small signal model of the transistor. Again, just to summarize, this is just the model of the transistor by itself. It's a model of the transistor by itself. Later on, when we connect components to the transistor, then you're going to have to recompute for the small signal parameters, or rather the two-port parameters of your new network. Kasi magkakaroon ka ng bagong network, no? When you start adding components, you're going to have a new network, and you're going to have to compute the parameters, the two-port network parameters of that new network. But at least you have a baseline to work with, and the baseline to work with is your transistor two-port network equivalent. And that's what you're going to be doing for Module 5 and Module 6. Where in Module 6, the extra complication of high-frequency analysis is going to come in because your capacitors now are going to come into play. Again, this is the way I present it, but if you take a look at the lecture of Dr. Tess, no, it's more rigorous in terms of the mathematics. So the way I presented it, I guess, is a little bit more intuitive. I just felt that maybe you get a better feel if intuitive lang muna, tapos makita nyo yung yung more rigorous presentation. So that's all I wanted to talk about. I'll close the session as soon as the last person leaves. Thank you.
Thank you po, sir.
Thank you,
Yes, sir.
Thank you, sir. See you po sa Tuesday.
Okay. Yeah.